Okay, so B3, right? So in this problem right here, what we're going to do is we're going to use, solve a few problems with this equation, right? So we have solid lead carbonate converted into lead oxide solid and CO2 gas. We're given a table that has the delta H, delta S, and delta G formations for all three of those elements. And so the first question is calculate the delta G naught for this reaction, and then is the reaction spontaneous? So all we have to do is use Hess's law in this case. So if we go through, and this is going to be awkward, but whatever. All right, so if we go through, right, we have delta G. If we use Hess's law, so we first add up the delta G formations for both of the product. So we have the lead oxide, so that is negative 187.9, right, plus negative 394.36, right, and then we have our reactants, right? So that we subtract that out to the negative 625.5, right? And so then all of these things have the units of kilojoules per mole, right? So I'm just using a little bit of shorthand here, right? So kilojoules per mole. So we take that, plug this into our calculator, right? So we have negative 187.9 plus negative 394.36 minus negative 625.5. And so what we get is positive 43.24 kilojoules per mole. So if we look at that right there, right? So the delta G value is positive in this case, right? So delta G naught. And so positive delta G values are non-spontaneous thermodynamically, right? Only things that are negative are going to be spontaneous. So non-spontaneous. Next, right, it says to calculate the equilibrium constant at 25 degrees Celsius, right? So now all we have to do is use that the equation that we have, right? So we have the delta G naught is equal to negative RT natural log K in this scenario, right? And so the K is what we're trying to get at. So if we rearrange this equation, what we get is natural log of K is equal to negative delta G naught over RT. We just simply take both of those to the power of, or do e to the power of those things to get rid of the natural log on the left side. So what we end up with is K is equal to e to the power of negative delta G naught over RT in that scenario, right? So that's the equation that we're going to be using then to figure out what K is at 25 degrees Celsius. And so all we have to do is just plug in our numbers, right? So if we just simply take K, in this case, we have E, and then up here negative. And so now we have the delta G naught. We already calculated that right here. Now, one important thing to pay attention to is that R is typically given as 8.314 joules per mole per Kelvin, whereas the delta G value that we have there is in kilojoules per mole, right? And so they're at different scales. So the easiest thing really to do is just simply multiply the delta G value by 1,000 to get rid of that kilogram or that kilo prefix, right? And convert that into joules, and then everything should be on the scale that it needs to be. And so if we do that, what we have then is 43,240 joules per mole. Divide that by R, right? So that's going to be 8.314 joules per mole per Kelvin. And then we just multiply that by the temperature, right? So that's 25 degrees Celsius. Convert that into Kelvin. What we have is then 298 Kelvin. Right? So we have all these numbers. And so, joules and moles cancel right here, right? Kelvins cancel. So everything is unitless the way that we want it to be. And so now we have that. So all we have to do is plug it in. So we have E to the power of, right? And so one thing too, right, is that if you have one of these, TI-85 calculators, you can see which one is E, right? Is the blue button above the natural log thing right here, right? So all you have to do is hit the second and then the natural log, and then you get E to the power of whatever you want to put in. And so what I want to put in then is negative 43,240 divided by 8.314 times 298. And so what I get then is 2.63 times 10 to the 8th. Sorry, 10 to the negative 8th. In this case, right? And so if I look at the key real quick, this is what, B3, right? 2.633. Yeah, that's what I had in my calculator right there, times 10 to the negative 8, right? So that right there is what the K value is. That's how you would calculate it in this scenario. So, part C, right? So what is the equilibrium pressure of CO2 under these conditions, right? So first things first, we want to write out what the equilibrium expression is. And so if we look at it, right, what we see is that we have as a reactant solid lead carbonate, as a product solid lead oxide, and gaseous CO2. So there's only two things that are ever included in equilibrium expressions, and that's things that are in the gas phase and things that are in the aqueous phase, things that are dissolved. You don't include solids, you don't include liquids, right, because their activities are equal to 1. So those drop out. So the only thing that we're going to end up in our equilibrium expression, right, is just going to be the CO2 gas. And because it's a product, right, it's going to be in the numerator, right? So essentially, right, K is just simply going to be equal to the concentration of CO2, right? That's going to be our equilibrium expression right there. We know what K is, right? We just calculated that, right? That's 2.63 times 10 to the negative 8th, right? And so typically you use bar in those scenarios, right? Where how you calculate K and stuff. But you can also use atmospheres, right? Atmospheres, bars, they're pretty close, right? I mean, it's only like a 1% difference between the two of them. But I always write down bar, but if you know, ATM is okay as well. You're close enough, right? You're within 1% of that right there, depending on how things have been going in lecture for that part. So, excuse me. Right, but that's all you have to do right there, right? So the K value is going to be directly equal to the concentration of CO2. Part D, right, at what temperature does lead carbonate spontaneously decompose, right? And so the way that we do this is just strictly a thermodynamics problem now at this point, right? Because what we're looking for right now, right, delta G naught is going to be a positive number right now, currently, right? Meaning that it's not spontaneous, it's not going to decompose on its own, right? There has to be some kind of driving force that pushes it in that direction. But you can change the temperature of all that potentially, right? Depending on how the delta S and the delta H values work its way out, right? Because, based off of things that we've done in the past, right, we can easily figure out at what point an equilibrium is going to shift, right? At what point is the reaction become spontaneous? And that has to do when, just using the simple equation, right, where the temperature is equal to delta H over delta S, right? That's going to give us the temperature at which point something is going to become spontaneous for that reaction to become spontaneous in these scenarios. So we just need to calculate what the delta H and the delta S are in this case. We can do that, right, because in the previous table, we're given those values. So all we have to do is use Hess's law again. So now we just simply do delta H, right? And so we do products first, add those up, subtract out the reactants, right? And then when we get what delta H is. And so in this case right here, right, delta H is going to be equal to negative 217.3 plus negative 393.51, right? So that's the lead oxide and then the CO2 gas, and we subtract out the reactant, lead carbonate, which is negative 699.1, right? And all of these are just simply, the units have kilojoules per mole. So we take that, plug that in, so we have negative 217.3 plus negative 393.51 minus negative 699.1, and so what we get is 88.29 kilojoules per mole. Do the same thing now for the delta S, right? So if we plug those numbers in, what we have is 68.7 for the lead oxide plus 213.63 for the CO2 minus 131.0 for the lead carbonate, and all of that has the units of joules per mole per Kelvin. So we plug all of that in and calculate it. So we have 68.7 plus 213.63 minus 131. And so what we get is 151.33 joules per mole per Kelvin, right? And so now the important thing is, again, scale-wise, the delta H and the delta S aren't on the same scale, right? Delta H is kilojoules, whereas the delta S is in joules. And so for things to cancel out properly for that temperature, right, we just have to scale them properly. The easiest way, again, in my mind, is just simply multiplying the kilojoules by 1,000. So that way everything is then just simply in joules per mole and so forth, right? So now all we do is we take the temperature. And so we take that 88,290 joules per mole, divide that by 151.33 joules per mole per Kelvin, right? So joules per mole cancels, the Kelvin gets dropped up, and we just simply do the division. So 88,290 divided by 151.33 gives us 583.4 Kelvin, right? So that's the temperature at which the lead carbonate spontaneously decomposes in this case, right? Which I believe matches what I have here, right? 583.5. Yeah, same thing. Probably sig fig something somewhere. So yeah, so that's how you do B3 in this case right here.